Hi, students, and welcome to today's lesson. I'm Mrs. Davis. Today, we will explore the question, how do light rail trains start moving? Are you ready? Grab your pencil and your science journal, and let's get started. Remember the dark rail system from our last lesson? Engineers designed dark rail and other light rail systems to move people from place to place. We use this video to create our class model. Our model shows the train itself and the forces that affect the train's motion. The train starts to move forward because the force pushing the train is stronger than the backward force of friction. Imagine you are an engineer. How can you find out more about the ways force affects a train's motion? Maybe you said we could do an investigation to model how a train moves. I think that is a great idea. Today, we will plan an investigation to answer the question, how do light rail trains start moving? Let's use what we know about force to develop our claim. Think of a time you used force to make an object start moving. Maybe you kicked a soccer ball or pushed a toy car. Last summer, I went to the beach and pulled a wagon, but the sand made it hard for me to pull the wagon at a fast speed. Remember, speed is the distance an object moves in a certain amount of time. How can you make an object start moving with a faster speed? Well, if the object is a soccer ball, you could kick it harder to make it move faster. And pulling my wagon with more force made it roll faster. I wonder, how does the strength of a force affect the speed of a train? Let's use this question as our investigation question. Now, let's make an initial claim to answer that question. What should our initial claim be? With our soccer ball and wagon examples, a stronger force caused the objects to move faster. Do you think the same thing happens with a train? Maybe. I think our claim can be a stronger force causes a train to move faster than a weaker force does. How could we test our claim? I know, we could measure how fast a train model moves with a hard push and then with a gentle push. Then we could compare the results. We will use a spring scale, a Hall's car, and a meter stick to investigate our claim. Let's talk about the spring scale first. A spring scale is a tool that can be used to push an object with a known amount of force. We will use the metal loop to gently pull back the spring. Pulling back the spring allows us to set the scale to a particular force. Scientists measure force in units called newtons. Do you notice the capital N on the scale? This N stands for newtons, and this label indicates that this scale measures 0 to 5 newtons. When we set the spring scale to a particular force, we're setting it to a certain number of newtons. When we release the handle on the spring scale, the spring releases and the rod. The rod will push the Hall's car using the force we set on the spring scale. We will use the meter stick to measure how far the Hall's car moves. For our investigation, the Hall's car will represent the train model. Let's continue planning our investigation. But first, let's make sure we are conducting a fair test. In a fair test, we compare multiple items or conditions. In our investigation, we are comparing forces of different strengths applied to a train model. We also need to be sure we only change one variable at a time. What variable will we change in our investigation? The strength of force, right? We will use the spring scale to apply different strengths of force to the train model. We will need to keep all other variables constant. That means we will use the same setup and distance in each trial. In order to ensure we are conducting a fair test, we also need to collect data and complete multiple trials. What data will we collect? Well, we want to know how the strength of a force affects the speed of a train. Our claim is that a stronger force causes a train to move faster than a weaker force does. If the train model is pushed with a stronger force, it will move faster. When the train model moves faster, it will take less time to travel the same distance. I think we should document travel times. This will let us know if the train model is moving faster when more force is applied. How many times should we repeat this investigation? I think at least 5. Do you agree? We are off to a great start. Let's think about our investigation some more to make it even better. In addition to the spring scale, the train model, and the meter stick, we also have a stopwatch and masking tape to use for our investigation. What data points related to speed can we collect with the tools provided? I think we can measure distance with a meter stick, and we can use a stopwatch to measure time. The stopwatch can measure how many seconds the train model takes to travel 100 centimeters or the full length of the meter stick. We can use the masking tape to mark a finish line. We can make 100 centimeters the finish line. But wait, can every push always move the train model across the finish line? I tested pushes of different amounts of force. Pushes of 2 5/10 newtons don't always make it to the finish line, but pushes of 5 newtons always makes it across the finish line. Because weaker forces like 2 5/10 newtons don't push the train model the full 100 centimeters, let's use 3 newtons, 4 newtons, and 5 newtons for our investigation. How can we be sure to apply the same amount of force in each trial? We need to make sure the spring scale is on a flat surface and that the spring scale doesn't move when the rod pushes the train model. The test will only be fair if the spring scale is in the same place for every trial. I know, let's use some masking tape to tape the spring scale to a flat table. The masking tape will keep the spring scale from moving when we use it. I have one more question about our investigation for you. How can we make sure we collect time measurements consistently? We are going to use the stopwatch to collect data, right? But how will we know when to start and stop the stopwatch? I have an idea. I can count down from 3. I'll say 3, 2, 1, start. When I say start, we will start the stopwatch. Then, when the train model crosses the finish line, we will stop the stopwatch. Let's measure to the nearest hundredth of a second for each of our trials. I updated our fair test criteria chart using our investigation plan. Your task after this lesson will be to complete the fair test criteria chart. I also created a data table for our investigation. This is where we will record the strength of force. Let's fill in each strength of force. 3 newtons, 4 newtons, and 5 newtons. Great. This is where we'll record the time it takes the train model to travel 100 centimeters. Let's label this section time to travel 100 centimeters. How many trials will we complete? 5, right? Let's label each trial. What else should we include? Let's label this column for the middle number from our trials. In our next lesson, we will learn a method to analyze our data by selecting one number to represent each data set. Let's look back at our fair test criteria and think about our investigation plan to make a prediction. How do you think forces with different strengths will affect your train model? Do you think a stronger force will make the train move faster? Maybe. Which of the fair test criteria do you think will be most difficult to meet? Why do you think that? I think we might make a mistake when we are using the stopwatch or the spring scale. And if our table or floor is uneven, it might affect the results. Keeping all other variables constant is going to be tricky. Our investigation does have some limitations. Planning fair tests require effort and experience. We've done a great job planning a fair test today. In our next lesson, we will conduct the investigation and collect data. I can't wait. Let's review your task for today. Complete the fair test criteria chart.